we're digging deeper and breaking some forces down into its more elementary parameters. So the first one was regarding gravity, and we completed that. The second one was friction, we completed that. And last class, we also looked at drag. There is one more that we need to cover, but it's going to be much shorter than the first three, because this is going to be the focus of one of the labs, essentially the lab next week, as long as I don't have to randomly cancel, well, not randomly, but I don't have to cancel one of the labs. And that last one is going to be the spring. Call it FSP. And so I'm just going to go over very, very briefly just to give you the general idea and some major or the biggest comments about that. So let's look at a scenario of a spring that is attached to the wall. For a spring, what's very important, and let's say it's a frictionless surface, what's important is for you to identify what is called the equilibrium position. So XEQ. For the spring, this equilibrium value is very, very important, because this is the position at which the spring that's like the slowest moving bike or the longest driveway. So XEQ is a position at which the spring is neither compressed nor stretched. So at this point, at XEQ, the force of the spring is going to equal 0, because it's not stretched nor compressed. But from your years of experience with springs or rubber bands and things like that, I'm sure you'll be able to follow. If the object was positioned slightly to the left of XEQ, then the spring is going to push against it. So it's going to exert a push force. Whereas if the object was placed slightly to the right, then the spring is going to be exerting a pull force. And I'm sure you can also follow along with this. The further left you position the object, or further right you position the object, the stronger the spring is going to act against you. So we can say that the force of the spring is somehow related to what is called delta X. This is the position minus the equilibrium position. This just means, is referring to the deviation from your equilibrium point. The deviation from equilibrium point. So further you place it outside of the equilibrium, the harder the force the spring force is going to be. And there is a negative, because the spring is always going to be acting against you. As soon as you begin to displace it from the XEQ, the spring is going to try to push it back to that equilibrium position. If you stretch it further out, then the spring is going to pull and try to get it towards that equilibrium position. And so this negative needs to be there, because the spring is going to be opposing the deviation from XEQ. And we're just missing one term, and that is this constant K, where this K is defined as the spring constant. I'm sure you recognize not all springs are the same. Some are metallic, and slinkies can be plastic, and they can also be approximately springs. And they vary in this spring constant. This is essentially the strength of the spring. Some are very easy to stretch, some are very hard to stretch, or some are very easy to compress, others are very difficult to compress. And that's encapsulated by this constant here. And this has units of newtons per meter. Has units of newtons per meter. So you'll be seeing spring problems either like this, or an alternate way to do it would be to hang the spring vertically. And of course, when you bring it down and release it, then it's going to just bobble up and down, and so forth. And that's pretty much all I want to say about springs. You'll delve much deeper during one of the labs. But what we're going to turn to is we're going to add a level of complexity onto the types of problems that we've been doing up to this point. So we're going to be looking at what are called interacting objects. Now, before this section, we only considered single objects. We did not concern ourselves with many different things going on at the same time. We looked at a ball, or the cannonball, arrow, things like this. But now we're actually going to be considering multiple objects in a single scenario. So now we're going to add complexity by considering interacting systems. Yeah, question.
Sorry, just for a second, can you please just go back up to the force of spring equation? Thank you.
By considering interacting systems.
Thank you.
One second. And my screen is not. So let's look at a simple scenario that actually has interacting objects. A classic example would be a hammer hitting a nail. So let's say we have this wall, and there is a nail that is ready to be hit. This would be the hammer. We'll call a hammer object A and the nail B. When the hammer hits the nail, what is actually going on? At least in terms of the forces. The hammer, or object A, exerts force on object B. Actually, let me move this out of the way slightly. So when they make contact, the hammer exerts a force onto the nail. But at the same time, the nail, or object B, exerts force on hammer, which is A. So in a single instant, there are two different forces that need to be considered. One is making contact, hammer exerts a force on nail, and nail exerts a force on hammer. So we need a method of distinguishing between these two forces, and we do that with the use of subscripts. This is force of A onto B, so this is read as the force of A onto B. So the last subscript is the force on the receiving end. Then the force the nail exerts on the hammer would be F BA. F BA. And we can go even further and begin to draw what the forces may look like. When the hammer hits the nail is going to experience a force in this direction. And so we'll label this force of A onto B. It's the nail that experiences a force in this direction. Now, when it makes contact, the nail is going to exert a force onto the hammer, and the hammer is going to receive a force towards the opposite direction. This would be force of B onto A. Now this is an example of interaction, which is the mutual influence of objects on each other. And these interactions are of great interest to us. So here, the hammer influences the nail, but at the same time, the nail influences the hammer. That is an example of interaction. One thing to note is that these are not limited to two objects. Not limited to two objects. Now, because we have multiple objects inside the scenario, we have to do something to not confuse which object we are discussing. And so it's important to keep in mind what is called the system. The system is the object or objects whose motion we want to analyze. So by the system, this is referring to the objects we actually care about. Then there's the other group, other category, which we call the environment. Sometimes it is called the surrounding. And it's anything not in the system. Uh-oh, I gotta start my software over. 1 second. I gotta clean my screen. Give me one. Now, comment to make about systems. And this is where things get really fun, let's say. You need a free body diagram for each object. So this is where we're going to be, really increasing the complexity of free body diagrams, and when we can actually get into really interesting scenarios. Because we're going to be drawing multiple objects, we are going to connect the interactions on the free body diagram. We are going to connect them. So, what that means is I know we are missing the force of gravities on here, but what we mean by connecting is literally draw a line that connects the interacting force. So this is what we wanted to do. Now, I mentioned this before, but I'll mention it here again because it is here where it becomes more relevant, and it is here where people make more mistakes regarding the statement that I'm about to make. And it is that free body diagrams include forces acting on the object. On object, not by the object. On the object, not by the object. One additional thing, one of the things that we can do is ignore the Earth. Like, we don't include Earth as one of the objects in our system because it's just so massive. I'm getting a few texts here. Let me make sure I'm safe. So we're going to ignore the Earth because it, quote unquote, cannot move. Now, I know it moves. What this means is we can't actually make any meaningful movements about the Earth. We can try to jump on it, stomp on it all we want, but the Earth is too massive for us to actually make any meaningful impact on its motion. Now, with this in mind, with this interaction idea in mind, let me ask you a question. You guys do this every single day, many times a day, so you guys should be experts at this. And the question is, how do you walk? How is walking even done? So let me guide your thoughts in a little bit. When you're walking, or let's say when you begin to walk, you're standing still and you're walking. Because you're going from velocity equal to 0 to velocity is positive, you are accelerating, right? Then Newton's law tells us that there must be some force pushing you forward. Everyone follow? Well, what is that? How does that happen? So think there must be some F net pushing you forward when beginning to walk. To further guide our thoughts, let's draw the free body diagram. But let's choose a simpler scenario. Let's consider a crate. Let's consider a crate sliding. So let's say we have a crate and we have some speed v naught or v in that direction. What is a free body diagram here? Oh, you have the force of gravity, right? It's on a flat surface, so we have a normal force up. Because it's sliding, there will be some frictional force in that direction. Oh no! I have to restart the software again. All right. Now, in contrast, let's consider a person walking. Person walking. And same scenario. What is a free body diagram acting here? And think, how do you walk? How are you able to move forward if you're trying to move forward? What are you actually doing? Yes.
Is it like a static friction on the floor?
Which direction?
The arrow would be pointing left.
So, well, we have force of gravity. Let's get this one out, and also the normal force. So if you're walking this way, how do you walk? What are you doing?
There's static friction, but it's going left because you're pushing.
Yes, to walk that way, you're doing what? You're literally kicking the ground the opposite direction. Have you guys never walked before? So you would be walking by doing F push, right? You're pushing backwards. This is wrong! If you drew this, you are mistaken. Oh, wait, hold on 1 second. You gotta restart. But why is it wrong? No, that's not the reason why it's wrong. If you drew this, then you did not heed my words. A free body diagram includes the forces acting on the object, not by the object. That free body diagram, if you included the F push, that is what you are doing, not what you are experiencing. You are kicking the earth back. But when you kick the earth back, as Sam was saying, you get kinetic friction and the earth actually pushes you forward. So the proper free body diagram would have been this. This is what you are experiencing, not the normal force. There would be a static force coming from the earth. We have to remember the free body diagram is only the forces that the object is experiencing, not what you're actually doing. So this is actually an example of propulsion. So another way you can write this is simply write this, F propulsion.
Would you take either?
Yes, but I would say the static friction is a little bit more precise. So let's answer the question officially. How do you walk? To walk, you push the earth back. The earth via Fs pushes us forward. Then we switch feet. And so therefore, walking is an example of interaction. So even stuff that you may not be aware of, yes, that is an interaction. So understanding how objects interact is of great value and of great importance. Now we're going to talk about interactions in a very general sense for now. And by that general sense, what I mean is we are going to learn how to draw the free body diagrams properly. So let's do an example. A truck, let's say, pulls a car on horizontal road. We're tasked with identifying all objects, interactions, and we want to draw the free body diagram. So the scenario is going to look like this. We have a car, we have a rope, and then we have a truck. So we need to identify all the objects. How many objects do you see? These have to be meaningful distinctions. How many objects do you see? Yeah, Maddie?
3 if the rope counts as one.
3 if the rope counts as one, but that's my question to you. Does it count as one? Okay, yes, it does. So we would have the car, the rope, and the truck. So the objects, 1 is a truck, 2 car, 3 rope. So how many free body diagrams do we need to draw? Yes, we need 3. We need 1 for each object. So we need 1 for, the car, let's draw it very similar to the arrangement of the actual objects. So car, rope, and then the truck. So let's begin with the car. We're going to have the force of gravity on the car, so we have the force of gravity. Well, we have 3 different objects, so we can't just call it Fg. Because we have 3, we're going to have 3 different Fgs, so we need to use subscripts to distinguish. This is the force of gravity on the car. It's on a flat surface, so there will be the normal force up. But normal force on what? This is of the car, so we need to specify again. There's a normal force on the car. What else? What other forces are acting on the car?
Is there tension?
Tension, which direction? positive x here. The tension. On the car! But where's it coming from? It's coming from the rope. So the proper notation for this would be tension from the rope to the car. TRC. And let's say there's some friction, so we would say this would be the friction on the car. We're not really specified if the wheel is rolling or if it's sliding. We don't know that, so let's just call it lowercase f for friction on the car. Now, as soon as you see or you realize you wrote two different subscripts for objects, this should be an immediate sign to you that that is an interacting pair. So the rope is going to be experiencing a tension force from the car. So this will be TCR. And TCR. What other forces are acting on the rope?
Is there also tension in the other direction
From
from the truck?
From the truck, so it'll be T. What are our subscripts?
TC.
Not TC, because then that'll be the truck onto the car.
So CT.
That would be car onto the truck.
What? R?
TR, truck onto the road. Truck onto the road. Anything else? Yeah.
Gravity.
Force of gravity. FG. And then it would have to be on the rope R. Anything else? That seems like a no. Let's move on to the truck. We have the force of gravity on the truck. We also have the normal force on the truck. What else?
Tension.
Tension from the rope, so it'll be called what?
TR.
T, not TR, that's already here.
RT.
RT is correct. Anything else?
Friction.
Which direction?
The same direction as tension from same direction as tension of the rope on the truck, so like towards the left.
Incorrect. Because the truck is the one that's actually pulling, meaning there must be some forward force on the truck, right? And that comes through friction. So we have the static force on the truck is actually what's making us go forward. Essentially, this is the F propulsion. The propulsion from the truck. Yeah.
Doesn't the normal force be to say?
Oh yeah, that's correct. Does that make sense?
Would there also be F push? Or
No. This is what's propelling the truck forward. Except this is wrong! Alright, because we didn't connect the interactions. You have to remember to connect the interactions. Alright, except I lied. This is actually wrong. Even with that. Can anyone spot why? Technically, all of your assessment has been correct, but we are led to a contradictory scenario.
Is gravity all connected?
No, gravity is not all connected. So we're ignoring the Earth. Technically, this should be connected to the Earth, that should be connected to the Earth, but we're just ignoring the Earth because it's so massive. The issue is right here. Can anyone see it?
normal force?
No, it's not touching the ground, so there would be no normal force.
So that's what
Because-
force is.
Right. The rope is not touching the ground whatsoever. How were you guys?
Is it that the forces are exactly equal, so it wouldn't be going anywhere?
No, no.
Is the rope modeled as being light, so it wouldn't have any weight?
Okay.
Force of gravity.
Yes. There's this. Right now, what is the net force on the rope? What direction? It's down. The horizontals, they may cancel, but the net force is down. Meaning, in this scenario, if that is actually the free body diagram, guess what the rope is doing? Literally dropping straight to the ground. But that's not what it's doing, is it? It's actually holding or connecting the car and the truck together. So, what's actually occurring is on the car, we have the force of gravity, that's correct. We also have the normal force on the car, that's correct. We have the frictional force on the car, that's correct. But if you guys know anything about ropes, they are never ever perfectly horizontal. It goes down at a slight angle. Do you guys know what I'm talking about? So this would be the tension of the rope onto the car. And when we draw the free body diagram of the rope, the truck is pulling the rope up slightly at an angle. And so this would be the tension of the car onto the rope. So both the truck and the car are pulling it up, and force of gravity on the rope is down. Of course, we still do need to connect them. Such. Force of gravity on the truck, the normal force on the truck, propulsion force, as well as that little tension guy from the rope to the truck. This would be the correct free body diagram. And so ropes always have a little slack because of the weight of the rope. Now, one of the things that we're going to assume in the future, this is going to make the problem so much more complicated for pretty much no reason. So one of the ways around that is to simply say the mass of the rope is negligible, force of gravity is approximately 0, and at which point the tensions are going to be perfectly horizontal. Okay, so we will be invoking that in just a moment. But in terms of doing a full free body diagram, this is incorrect. This is actually the proper one, and I believe there is a problem in the problem set that actually has you do this once. It's just trigonometry, cosine, sine, stuff like that. Yeah.
Well, so how would you know whether friction acts? How would you be able to tell in which direction friction acts?
So this is the propulsion friction. There is a alternate friction. I guess technically you were correct. There would be an alternate source of friction that's holding you back, but it would be the rolling friction. It wouldn't be the static. Because the static is actually getting you to move, but do your wheels spin for free? Or is there some friction due to the bearings and stuff?
Right.
Right, and that would be the rolling friction. That would be what's going backwards. But it's not static.
Right. Okay.
Does that make sense?
Yeah. Well, so regardless of whether the truck is connected to like other objects or not, you'd still have like static friction like pointing in that direction, in the forward direction.
Correct. Because, well, when you're driving, think about how a car drives. We thought about how we walk. We are pushing the earth back, right? When a car is driving, the wheels are pushing the earth back, but the earth is then using that to push the car forward. Does that make sense?
Yeah, that does make sense.
So that's why these static frictional forces here, and I think this answers your question that you had in the problem set, because it's pretty much the same thing. All right, but we're going to keep talking about it. Give me 1 second.
Thank you.
Now there's a question.
Is theta consistent throughout the whole?
This theta and this theta is the same, but this theta and this theta are the same. But this and this doesn't have to be the same.
So I guess I'm so confused because if a truck's pulling the other car, often if a rope is like, if there's big retention, then it would fully be straight.
It won't fully be straight. If you zoom in with a microscope, you will see that there is a little bit of slack.
Okay.
Yeah. It might look super duper straight, and I agree. Sometimes when you have so much tension, it will be, but there is always a little bit of slack. Now there's question.
Does that mean that at T max theta is gonna be 0?
Wait, what is like max tension?
Yeah.
Yeah, at max tension, that's when it approaches theta equal to 0. Yes. Yeah. But it's never actually equal to 0. That's why it's called the maximum. At infinite force, then you have it, but there's no such thing as an infinite force. Of course, at infinite force, the rope will also break, so you get a lot of different conundrums at that point. Now, there's a reason why we are actually connecting the interacting forces. And that's because of Newton's third law. Now we can talk about his third law, Newton's third law. Most people know it by word. Newton's third law states that for every action, oh yes, you guys all know it. So for every action, there is equal and opposite reaction. Well, this is not an English class, so we want to come up with a mathematical formulation that captures the same thing. And that is simply this. Force of A onto B is equal to the negative of the force of B onto A. For every action, that's FAB, there's a equal and opposite reaction, so this is equal to negative, that's the opposite reaction, FBA. That's what this, mathematically, that's what Newton's third law stipulates. This is third law. Now, these are equal and opposite forces, not acceleration. Not acceleration. And the reason why I'm saying this is because when objects are interacting, they not only have what is called the third law relationship, but they could be interacting in a few other ways. Ways that do dictate the acceleration. So, however, there can be acceleration constraints. So the third law doesn't say anything about the acceleration. However, just analyzing the scenario, you can still come to some conclusions about the accelerations and how interacting objects would have, accelerations that are meaningful with respect to each other. One such example would be the free body diagram that we just did. Towing a car example. So let me redraw the scenario. We have car, we have the rope, and we have the truck. How many objects do we have? We have the car, we have the rope, and we have the truck. We have 3 different objects, meaning each object can accelerate with its own acceleration value. The car has an acceleration of AC, the rope has an acceleration of AR, and the truck has an acceleration value of AT. In this example, when the truck is towing the car, how are the accelerations related?
They're all the same.
Right, they're all the same. Whatever the truck is accelerating with, the rope has to accelerate with because it's connected. Whatever the rope and the truck are accelerating with, the car has to accelerate with that same value because all these objects are connected. So this is a relationship that we have not arising from Newton's third law, just by the fact that they are connected. Okay? So because they are connected together. This is called the acceleration constraint. So when you're talking about multiple objects, there's a few things that you do have to consider. Are they exerting interacting forces? The second thing you need to consider is, are they connected in some fashion? Because if they're interacting, you know some information about the forces, and if they're connected, then you know the information about their accelerations. Now with that in mind, let's try a slightly different scenario. Let's say we have a pulley, we have an object and an object B. Let's say object B is falling down. What is the acceleration constraint for this scenario? What is the acceleration constraint?
A? Would it be just that it's constrained by A?
Yeah, but what is the specific relationship? So this was the acceleration constraint for this example. What is it for this example where we have objects A and B? How are the accelerations related? Sam.
Would the acceleration of A be equal to the acceleration of B because they're connected by the rope or the pulley or whatever?
What do you mean they are the same? Do you mean the magnitudes are the same? Remember, acceleration is a vector, so they're going in different directions, so it can't be the same in that sense.
Right.
So what is the same then?
Yeah, it would be the magnitude. 'Cause
Yes, one of the things that's true is the magnitude of the acceleration of A is equal to the magnitude of the acceleration of B. Because whatever B does in terms of moving, A will also be moving. However, this is not the most precise we can be, and this would not be a sufficient acceleration constraint. You guys have identified the magnitudes are the same, that's true. However, this is not the precise acceleration constraint. Instead, we need to specify the coordinate direction. This would be x, this would be y. Then the acceleration constraint in this scenario would be that the acceleration of A in the x direction, and it's going in the positive direction, positive x, is going to be equal to the negative of the acceleration in the y direction of object B. This would be the acceleration constraint for this scenario. Whatever B does in the y direction, or in terms of going down the y direction, is what A will do going in the positive x direction. Here are the signs of acceleration may vary. You have a question?
So the lines next to the acceleration of A equals the acceleration of A, I forgot what those are called. That makes.
This magnitude?
So why is one positive and one negative? That's just because one's X and one's Y.
So yeah, when you have a an object hanging off, force of gravity is going to pull it down this direction, right?
Got it.
So when it's going down, are you going in the positive or negative y direction? Right, negative. That's why this negative is here. But when this moves down, how does A move? Is that positive or negative x? Right, that's why this is positive.
So
Whatever this does in the negative, this will do in the positive x.
So in that sense, if A were to be going to the left,
Yes, if I grab this and then pull it over here,
yes, that would mean negative the acceleration of AX is equal to positive.
yes,
acceleration
negative
of YB.
ax would equal positive ayb. But if you just divide both sides by, or multiply by -1, you still get the same thing.
Right.
Yeah.
Okay, understood. Makes sense.
So now, essentially, I just gave you the tool sets of doing problems, solving problems where objects are interacting. Yeah, question?
So does it matter, for the AAX and like the AYB, does it matter which way we write it?
What do you mean?
Like how, for the first one, how it's the A, like the A's first?
This?
And then, yeah, and then the second one, the Y's first?
Oh no, it doesn't matter.
Okay.
So yeah, that is equal to ax. Yeah. So one is specifying the object, the other one specifying the direction. Right, there's little room for confusion on that one. It's when you're talking about the forces, then the order of subscripts are very, very important. Alright. So I just gave you the tool sets of doing very, very complex problems. So let's go over the problem solving approach, and then we will conclude today by doing a rather complicated example. But it's still on the simpler side of things. The problem solving approach doesn't really change in the first step. We are trying to assess the scenario. Right, you always have to be making sure you collected all the valuable information, understood all that information properly. So to do that, we want to use a sketch as well as a free body diagram. And of course, now, in our free body diagrams, we want to include the interactions. Include the interactions. And of course, we want to list our givens, the things that we know, as long also we want to precisely identify what the problem is asking for. So that hasn't changed one bit, except this idea of the interactions, but that's just part of the free body diagram. It's in the second step that we have to insert an additional step. In solving dynamics problems, you're always going to be using Newton's law. We already discussed how to employ Newton's second law, but this time we have to do it for every object. So if you have 3 objects, guess how many force balances you have to do? 3. Right? These problems can get extremely complex. So by this I mean the force balance is equal to ma mass times acceleration. Well, that's only second law. We can invoke Newton's third law now because we know what that is. And we invoke it for different interactions. And this reduces or increases the amount of information we know. So increased amount of info known. But this is not going to be trivial. This is where the problem-solving skill sets are going to come into play. Because you need to make a judgment call on, is it an interaction? If it's yes, is it useful? So there's a few things that you have to make a decision on in this step. But that's not all. We have that acceleration constraint that I was speaking of before. And here, your problem-solving skills are tested yet again. You need to assess, are the objects connected in some meaningful fashion? If yes, okay, then what is that specific relationship? In this example with the pulley, the relationship was when B is going down, A is going to the right, down is negative Y, right is positive X, so we actually needed to do that ourselves. Then, you apply the kinematic equations to answer the problem if they are even asking for a kinetic parameter, or kinematic parameter. So the overall scheme of things, the problem-solving steps don't really change. Assess the scenario, use Newton's laws, and then go to the kinematic equations. It's just we got a few additional steps in terms of actually doing Newton's laws. So let's put all of this together, and then we will call it a day. So let's say you have a 200 kilogram crate onto 2,000 kilogram truck. So the scenario we have is this. We have a crate and the truck. We are told FST propels you forward. That is the force from the surface to the truck. Force from the surface to the truck. So how we were to understand that would be that is FST. And this is how the truck is moving forward. The surface or the earth is exerting a force onto the truck so that the truck can go. The question we want to answer is, what is the max FST without the crate sliding? That is the question that we want to answer. So let's try to understand what the problem is asking for. If the truck accelerates, the crate is going to be doing what? Let's say it's accelerating pretty slow. The crate is going to be doing what?
On the truck bed.
Yeah, it's going, therefore, if the truck is moving that way, what's going to happen with the crate? Huh?
We just want to stay on that.
It's sliding back.
Okay, it wants to slide back, right? But we are asking without crate sliding. So we're accelerating pretty slowly so that the crate stays on the truck. So if the truck goes this way, then the crate is going to stay on the truck and it will also move that way, right? So what is the acceleration constraint in this problem?
Acceleration is equal.
Huh?
Acceleration is the same between
Yeah.
the truck and the crate.
Yeah. AC is equal to AT. and so we'll just call it a generic A. But if you accelerate fast enough, then the crate is going to fall off the truck. But we want to know what is that maximum acceleration value that the truck can accelerate at, such that it doesn't happen, such that this constraint is actually met. That's what the problem is asking for. And let's also say the static coefficient is 0.8, the kinetic is 0.3. So in the first step of the problem solving, we will want to begin with a sketch. Well, pretty much it was given in the problem. The next thing we want to do is draw a free body diagram for each one of our objects. So we have the crate and we have the truck. I'll give you guys a minute to try to draw the free body diagram with the interactions yourself. Right. How many interactions do you guys think there are between the crate and the truck? How many interactions? I see 2. Anybody else? Alright, apparently nobody else. Alright, 2 is correct, but let's see if it's the correct 2 that's been identified. First, we have the force of gravity on the crate, so we have to call it FGC. What other forces do we have? Yeah.
Normal force, but would the subscript be TC?
Yes, the normal force, the truck is now the one exerting the normal force up. The truck is acting like a surface to the crate. So it would be normal force TC. As soon as you write these 2 subscripts, you should know, oh, that's an interaction pair. That is a key for an interacting pair, meaning you're going to have an equal and opposite force onto the truck. So you're going to have the normal force of the crate onto the truck down here. Do we have anything else on the crate?
Static friction.
Which direction? So static friction, which direction?
It would be acting towards the right.
Yes, when the truck moves this away, the crate is going to move which away? That away, but how? How does it move? The truck exerts a static frictional force onto the crate. So it'll be FSTC. Static frictional force from the truck onto the crate. That is what will get the crate moving or accelerating with the truck. It is a frictional force that is pulling the crate along. But aha, over here, we wrote that TC again, meaning the crate is opposing the truck's motion with its static frictional force, so it's CT. And here we're going to neglect drag, so we'll do that. Neglect drag. What other forces are on the crate? Alright, I'll take the silence to mean none, and that is correct. But then what are the forces acting on the truck?
Propulsion.
Which direction?
Positive F.
Yes. But it's not called F propulsion because we were given it as the force of S on T. That's what we were given right here. So we were given what notation to use by the problem itself. What else? So yeah.
Gravity and then normal force.
Force of gravity on the truck and normal force on the truck. And of course, we need to connect the interacting pairs. We will connect that, and then we will connect that. And these are the two interactions, and this would be the full three-body diagram of our scenario. Question?
Does the truck not have its own kinetic friction?
Yeah, you can include that. That would have been okay. Actually, the problem, I didn't write this, but mu r of the truck was equal to 0. Yeah. So yes, technically there would be, here, we'll put it here for, there you go.
So that's just, it's like rolling friction.
Yeah, rolling friction on the truck. So this would be the free body diagram for the scenario. And this is a very typical one. And in the problems where you're going to have problems where the entire problem is for you to draw the free body diagrams, you'll get a lot more complicated or complex scenarios. But this is a rather simple one. In the problem solving steps, we also want to include what else is known. What are known? I'm going to combine the givens and the knowns. We know the mass of the crate. We know the mass of the truck. And you guys have correctly identified the acceleration constraint in this problem. Acceleration of the crate is equal to the acceleration of the truck, which we can simply just call acceleration A. This is true if no slip. If no slip. So at maximum no slip, we know that the frictional force from the truck onto the crate is going to have this value. All right, this is just coming from our friction section. Oh, sorry. FSTC is equal to FSTC max, and that is equal to mu s times the normal force N. So we have this constraint that's met. Then we move on to utilizing Newton's laws. We begin with Newton's second law. Remember, you have Newton's second law for every single object in your system, or every, So we have the crate. And the crate is a good place to begin because of the scenario. We're trying to understand when will the crate not slip. So, we're going to do the force balance in the x direction. So F net in the x direction is simply equal to we see there is only one force acting in the x direction. And that is Fs, static frictional force from the truck onto the crate, but that is going to be the maximum one. This is going to be equal to, from Newton's second law, mass times the acceleration in that direction. But we need to specify the mass as the mass of the crate. I gave you guys a warning at the beginning of the semester. You guys have to learn how to use subscripts, and now we are here. And if you guys haven't practiced it, well, you guys did not heed my warning, so I guess you'll just have to struggle through it. Which means the mass of the crate times the acceleration is going to be equal to this guy, which we know is the coefficient of static friction times the normal force of the crate, meaning the truck onto the crate. We know the mass of the crate. We don't know the acceleration. We do know the coefficient of static friction, and we don't know the normal force. Now let's be clear on what this acceleration value even means. This is of the crate, sorry. This is the maximum acceleration crate can experience without sliding. And we know that this is the maximum acceleration because we used the maximum frictional force expression. So for the normal force, we look onto the free body diagram and notice which direction the normal force is acting in. It is in the y direction. So we didn't fully exhaust our force balance. We can do the force balance in the y direction to get that normal force value. From the free body diagram, you see that you have the normal force acting in the y, as well as the gravitational force acting in the y. So this is going to be positive NTC minus force of gravity on the crate. And this is going to be equal to mass of the crate times the acceleration in the y direction of the crate. But let's look at the scenario, yeah.
What's the subscript E mean next to Y?
No, what? C.
Oh, C. Sorry.
If you look at the scenario here, is the crate accelerating in the y direction? No, it's not magically floating off into space or anything like that. So this is equal to 0. Meaning the normal force of the truck onto the crate, that is simply the force of gravity on the crate, or its mass of the crate times g. Here, then this expression becomes mass of the crate times the acceleration of the crate is going to be mu s times mcg. And what can cancel? Masses can cancel. So AXC is going to be mu s times g. And this, once again, is maximum acceleration of the crate possible without sliding. But is this what the problem was asking for? What was the problem asking for? What was the maximum value of the force on the truck? So all we did was get information about the crate. How can we utilize this information about the crate to get some information about the truck. For that, we can use the acceleration constraint. Whatever the crate was accelerating at, that is the acceleration that the truck was accelerating at. And so here we know that acceleration of the truck must also equal this. So then the question becomes, or the thought process becomes, what FST will result in AT, which is equal to mu SG? This is now the question that we want to answer. Because this will be the maximum force that the crate can experience without it slipping. So then for this, we want to use Newton's second law, because we see that the force of the surface onto the truck, that's just acting in the x direction. So let's just analyze the x direction for the truck. Now this is of the truck. F net of the truck in the x direction is going to be, we have the FST, but we also have the static frictional force from the crate opposing it. So minus FSCT, but then that's going to be the maximum value. This is going to be equal to mass of the truck times the acceleration of the truck.
Why is it Fnet TX and not TC?
Where?
For Fnet TX.
No, this is truck in the x direction.
Oh.
The net force of the truck in the x direction. So we simply rearrange this expression, FST, that's the value we're looking for, is mass of the truck times the acceleration of the truck plus the static friction from the crate onto the truck and the maximum value of that. Or broken down into its more simpler terms, MT AT plus mu S times the normal force of the crate, which is equal to the normal force we already computed was that it is mass of the crate times the gravity G. But the acceleration value we know is mu S times G. So then this would be mass of the truck times mu S G plus mu S mcg. And here, what parameters can we factor out? What parameters can be factored out? Mu S, yes. And G times MT plus MC. This is the maximum FST that's possible. Do we know mu S? Yes, that's given in the problem. G is always 9.8 with the correct units. Mass of the truck and mass of the crate, we all know. So then this is going to be equal to 0.8 times 9.8 meters per second squared times 2,200 kilograms. Which is equal to 17,000 newtons. And that will be the final solution. These problems are going to constitute a lot of steps, But when you guys get to the point where you can solve these, well, it should be very rewarding. Yeah, unfortunately, this is still considered on the simpler end of things, so.
Was
Yeah.
it 2,200 or 2,000?
Well, it's 2,000 for the truck and 200 for the crate,
Oh.
and so 2,200 is this stuff.